Hi, welcome everyone. Welcome to the first seminar of the IDEA AI seminar series in fall 2020. So the series will bring top AI researchers from around the country and the world to talk about their research vision and plans. So I'm delighted to have Professor Amy McGovern today from the University of Oklahoma. She's a Lloyd G. and Joyce Austin Presidential Professor in the School of Computer Science and the School of Meteorology there. She has been leading the development of artificial intelligence and machine learning techniques for weather applications for almost 15 years and has won many awards for her research. Most recently, she's now directing the NSF AI Institute for research on trustworthy AI in weather, climate, and coastal oceanography. So let's welcome Amy again, who will be talking about building trustworthy AI for environmental science. Thanks.
So as you said, I'm Amy McGovern, and I am going to talk, that is a lot of things on the first slide, but I was specifically asked to talk about the new NSF AI Institute for Research on Trustworthy AI in Weather, Climate, and Coastal Oceanography, which is, by the way, a short version of that name because that version of the name is quite long. So I want to, just because, about 45 minutes, I wanted to give you a roadmap of where we're going. We're going to talk about why we care about trustworthy AI for environmental science, and then we'll talk about the Institute. And then depending on time, I have a couple of research results that we can talk about as well. But this will depend on how many questions we answer and how much time we have. So I'm going to start with some motivation that I think everybody probably is going to agree with, which is that as our climate is changing, so for example, this is a tornado that's hit. This is some hail. These are actual photos that, so if I go back, that's a tornado from the southeast. That's hail. That's actually my hand. It's hail that fell at my house. As we're seeing impacts on the ocean, this is a sensing system that's deployed that's looking for harmful algal blooms. We have impacts on sea life. So there's a turtle there that they're working on rehoming and making sure that the turtle is, not dying out as a species. And turtles are very popular, so you can see the number of people there. And, as we have other impacts, such as this is a picture from last year. I could well have had a picture from this year where we have multiple hurricanes coming in. All of these impacts are changing as the climate is changing, and humans need to be able to adapt. The other species need to be able to adapt. So we need to be able to improve our resiliency as the climate is changing. And if you don't like just the picture-based motivation, if you just want to think about money, this is a picture of the billion-dollar weather disasters, and these are only from January to June, and we already have a number of billion-dollar weather disasters from this year. If they had updated this graphic, this is a graphic produced by NOAA. I went just like 10 minutes before the talk to see if there was a new version of the graphic, and they don't have one out that includes July, August, and September, but if they did, there would be additional disasters such as the wildfires. So we need to use AI to improve our resiliency to all of these events. And then you might say, okay, well, I can believe you that we need the resiliency to the environmental science because climate is changing. But why do we need AI? What is in it for AI? Well, one of the things that's happening is that we have a tremendous number of new sensing systems that are coming online. We have satellites, we have mobile radar trucks, we have crowdsourced data. All of this data is being provided at really high spatial and temporal resolution, and there's no way for a single human to sift through that data in real time. And so what happens is a lot of that data is ignored. The satellite data, for example, only about 5% of the data is actually stored and used. That means we're throwing away 95% of very valuable data. And then if we're going to have all this data coming in and we're going to have the AI system look through it, we need to be able to have the AI systems guide the end users, and our end users are going to be different kinds of end users, towards making different critical decisions, because they have to make, many forecasters have to make life or death decisions. Do you issue a tornado warning? Do you not issue the tornado warning? If you get it wrong, people are going to die. If you get it wrong and the tornado came, people may die. If you get it wrong and there was no tornado, people are going to laugh and say, you can't ever get this right. You have to decide what the right answer is. And on a larger scale, do you evacuate a city for a hurricane? You do that instead of a tornado warning scale, which is 15 minutes in advance. You evacuate, that's usually days in advance. I grabbed this picture because I gave a similar motivation talk to NASA, and one of the things they have to make is a go no-go for launch. So that's a picture from the SpaceX launch, the first SpaceX launch, where it was scrubbed at the last minute. All these end users make critical protective decisions. They need to decide at different timescales. Do you close your business or school early? Do you get into your shelter? Do you get on the roads, et cetera? And I want to make the point, because the trustworthy AI that we're going to talk about really cares about the end users needs differ very greatly. So what we're developing for our AI is going to matter about which trustworthy AI end user, or which end users are using our AI. So severe weather, which are the examples I gave here, typically it's forecasters, so other scientists. Forecasters are trained. It's emergency managers, but it can also include the public. And the needs of the forecasters differ from the emergency managers, and they differ greatly from the public. And then if you want to think even outside the domain of severe weather, which is more on the very short temporal scale, long-term, the seasonal to subseasonal, do we need to look at crops? And then the end users differ for crops. A corporate corporation that has millions of acres has different needs than a family-owned small farm. But both of them need to care about whether or not there's going to be a drought coming up, for example. So as was mentioned in the beginning, we have this newly funded NSF AI Institute with the very long name, the NSF AI Institute for Research on Trustworthy AI in Weather, Climate, and Coastal Oceanography. Our short version of our name is AI to ES, so AI to Environmental Science. There's an embedded math joke in that, but I will explain later if somebody wants me to explain it. Our partners are listed all the way around this slide. So we have OU as the lead institution. We have Texas A&M Corpus Christi, North Carolina State University, Colorado State University, University of Albany, University of Washington, and Del Mar College. And then, so those are our academic partners. And then we have NOAA as a government partner. And then we have private industry. So we have, NCAR is not private industry. NCAR is a federally funded research center. Didn't mean to forget them. And then we have the 4 private industries, so NVIDIA, Disaster Tech, IBM, and Google, and they're all partners, and they're going to be helping to both develop the fundamental research and move it into the public and the needs of the public. So AI2S is going to be uniquely benefiting humanity by developing novel, physically based AI techniques that are demonstrated to be trustworthy and will directly improve the prediction and the understanding and communication of high-impact environmental hazards. And I will say we have a webpage up if you want to go look more about what we're doing. It's not fully fleshed out yet. We've only been live for about 3 weeks. And we have a Twitter account. And again, we've been live for about 3 weeks, but feel free to go and follow our Twitter account. As we get more results, as we're spinning up, we will be tweeting and putting things onto the website much more. Right now, the website mostly lists who our partners are. And if you want to see any of the people, they're all on the website as well. So I was asked to talk more about what our center will be, or our institute will be doing. So I'm going to talk about it. I don't have results from the center because we've literally, we started September 1st, and this is September 24th. But we have 4 focus areas. So the first is the foundational research in trustworthy AI and machine learning. And I'm going to talk about each one of these 4 focus areas, at least on one slide each, so that you get a little bit more detail. I'm giving you the overview now. So we have the foundational research. We have what NSF is calling use-inspired research. It's often called, the work that you're working with domain scientists, but they called it use-inspired in environmental science. And then we have foundational research in AI risk communication for the environmental science hazards. And then finally, and I do not want to miss this because it's a critical part of our plan, because we are an institute, we have workforce development and broadening participation. And then all of that together goes to our institute, which we have a pretty logo, so I like to show it. So the foundational research in trustworthy AI and machine learning, we have 3 main goals. And so our goals are develop explainable AI methods that are aligned with environmental science domain perspectives and priorities. And what does that mean? Explainable AI is a up-and-coming technique where people are looking at the AI, particularly deep learning, and saying, this isn't a black box anymore. We really want to understand what's going on inside this black box. But the key for us is that we're aligning what we're doing with the needs of environmental science data, which is very different than typical AI data. It's not although there may be images, it's not image-based data. It's not IID. It's very highly spatially and temporally autocorrelated. And it has physical laws that govern it. You can't come up with an example, a plausible explanation out of your method if it violates the laws of physics, because nobody wants to use your method if it's doing that. So that brings us to the second goal, which is to develop physically based AI techniques for the environmental science domain. So we want to make sure that we are incorporating the laws of physics. I know that physically based AI is something that's also up and coming, and people have been talking a lot about it, and they mean different things with it. For us, we mean that we're incorporating the laws of physics. The third goal is that we're going to be developing robust AI techniques, prediction techniques, and then we're theoretically validating them. So when we say with adversarial data, we don't necessarily mean that there's going to be an adversary out there, but that data can be missing, and it could be intentionally wrong. We want to make sure that our techniques are robust. So I have a little bit more detail on each one of these goals. This is just some examples of some work that we've done on XAI and environmental science. So it's sort of the preliminary work version. The members of our group are the leaders in development of XAI for environmental science. And so I just have 3 examples here. The one on the left, and hopefully you can see my mouse. If not, I'm on the left-hand column where it says application 1. We're looking at trying to figure out how we can emulate radar imagery using deep neural networks. And then once we've emulated that radar imagery, and that, by the way, we can do emulating radar imagery from satellite data, where places where there isn't radar that you can actually sense, so that if you can learn what the radar should look like from satellite data, then you can essentially get radar readings where there isn't radar. And one of the things we're doing with XAI, and so in this particular method, it's a layer-wise relevant propagation. They're looking at what strategies it is that the neural network is using to derive its estimates, so that you can see whether or not the strategies are physically plausible. The one in the middle is looking at using a deep neural network, a convolutional neural network, for analysis of severe hail, and so predicting hail. And one of the cool things we did with this was we looked at what kinds of strategies were identified within the network. So looking using saliency maps to see what looked important, and then we looked at those and said these look like supercells. Those are in the little embedded window up here. They look like 3 different kinds of storms. A supercell, a bow-echo, and a pulse storm, and then we graphed it, like where do those storms appear, where are they highlighted by the neural network, and they match with what happens physically, that there's more pulse storms in the southeast, that there's more supercells in the southern Midwest, more bow-echoes in the upper Midwest. So it's really nice to physically validate that the AI learned something that you expect. And then the third one is looking at learning the real-time storm morphology with its CNNs as well. And I'm going to, in the name of time, I'm going to not talk about that one so much. Moving to the physically based AI techniques. So this is just an example on the right-hand side of just trying to say that we're using the laws of physics to create robust, primarily deep learning based methods that create, we can use physics constrained loss functions that can create neural networks that learn something that cannot violate the laws of physics. So we can hybrid together the physical models and the AI system predictions, et cetera. So we can create novel architectures for the deep learning that use the physics, and then use those to also feed back into the XAI system and make sure that what the XAI is showing is also physically possible. And then the third one, the robust AI, I just have some graphics from performance diagrams. So just showing so I'll just leave those there, that they're just showing different performance under different situations for predicting hail. The environmental data sets are often very, very limited. It's a strange world in the sense that there's a tremendous amount of data out there, and I said that in the beginning, and yet there's also limited data because there's a limited number of tornadoes, for example. So for those who know how many examples that deep learning likes, a really bumper crop of a year in tornadoes has 2,000 tornadoes in a year. And, just like 2 or 3 of those are going to be the really intense tornadoes. We need hundreds of thousands of examples for most of machine learning and for deep learning. And so the limited data, we have lots and lots of examples of no tornado, but we need to have examples of the tornado itself. So we have to deal with class imbalance. We have to deal with creating robust AI so we could train it on the common phenomena and transfer it to the rare events, make sure that it's actually still robust. Look at trying to label data when data is really hard to label, where it's expensive or it's unavailable. And just we want to provide theoretical guarantees for the robustness of the methods. If we're going to field them, then we want them to be guaranteed to say, for example, as an example of something that we have seen in the past, you don't want it to predict that something's going to be less than 0 Kelvin. That's physically impossible. You could just put a hard limit. Okay, if it's less than 0, I predict 0, but even 0 is unrealistic. We don't get to 0 Kelvin. So we need to have those guarantees that tell us that they're going to not violate the laws of physics. So this is a cycle of the research. The AI is based on embedded with the environmental scientists. The environmental science domains, we want to use the Trustworthy AI to predict actionable environmental science information, and we want to enhance scientific and physical understanding of the environmental science processes. So I want to talk a little bit about our domains. Our first domain is convective weather. So I know that the Southeast gets just as many thunderstorms as we do. It's a different kind of regime of thunderstorms than us, but you get a lot of convective weather. Thunderstorm hazards, so tornadoes and hail, produce billions of dollars of damage. They kill hundreds of people every year. And tornado warning skill really hasn't improved in the last decade. So our goal is to use this AI methods that we're developing to improve the prediction of tornadoes and hail and other convective phenomena. We're focusing on the tornadoes and hail first. And so I just have some pictures here. I'm actually, the last half of the talk, going to talk about the tornado results, and then the second half of the talk. So I have a third, let's call it. The last third of the talk is about tornadoes. The second third is about the hail predictions. But we've got results to prove that the both hail and tornadoes are predictable using the AI methods. Winter weather. So winter weather is a major hazard in the United States, and you might think, why is Oklahoma studying winter weather? Well, we have a lot of partners, and that's part of it. And part of it is that Oklahoma actually does get winter weather. So what we're going to be doing is we're going to be using things like the New York Mesonet and the Oklahoma Mesonet to create methods that can robustly predict winter weather across different parts of the United States, because New York's winter weather is very different than Oklahoma's winter weather. We typically get ice, they get snow. And we want to be able to provide tailored guidance to the end users. In this case, we're going to be looking at emergency managers. A third application area for the environmental science, tropical cyclones, also known as hurricanes. They have a tremendous societal impact in terms of damage and flooding, and we're trying to improve the understanding of the tropical cyclone evolution when they rapidly intensify, and we improve the understanding and the forecasting of the tropical cyclones. And I have a short example there where we've got some results showing that, we've got geostationary satellites where we can get views of the hurricane or the tropical cyclone every so often, every 10 to 15 minutes, but sometimes we can't see the internal structure. The clouds obstruct the internal structure. And so if we can use other microwave imagery that we do know and align that with satellite images, we can train a deep neural network to be able to reconstruct the microwave imagery that we can't get on a much more frequent basis, because we can only get the microwave imagery a couple of times a day, whereas the satellite can give us information every 10 to 15 minutes. So we can use XAI to do that and create those methods. So there are 5 different environmental science application domains, and this is our 4th one, subseasonal to seasonal prediction. So in the graph down here on the left, if you want to sort of ask the question between what's weather and what's seasonal, there's a gap. The weather events, typically we can do prediction in the minutes to 2 week time frame, although it gets harder and harder to do the prediction as you get down toward 2 weeks. It's really, really hard in the gap between 2 weeks and about 2 months. That's the S2S gap, to do decent predictions. And then there's a decent amount of skill at predicting seasonal outlooks. And we're looking in that gap at whether or not we can use AI to improve the prediction in that gap. And by doing so, try to also improve the science and the fundamental understanding of what's happening. So we have an example over on the right of looking at predicting regions relevant for the prediction of extreme rainfall in North America 18 days later. So you'll notice that the graph is not North America, the graph is Asia. They're looking for what's going on in Asia that's going to affect North America and create the extreme rainfall events in North America 18 days later. We have coastal oceanography. So coastal phenomena like the tropical cyclones, but there are other coastal phenomena we're going to talk about and we're going to work on, are impact humanity regularly. And so we can improve the prediction and understanding of these. We're going to save lives and property. So on this graph, we're talking about a couple of phenomena, ocean eddies, which are very large scale rotations that last months in the ocean, and they severely affect the oil rigs in the ocean. So they have to, because I've heard them called ocean tornadoes, but they're not a tornado in the sense that they're on a completely different spatial and temporal scale, but they still have a similar effect. So they need to be able to predict them, but on the larger time scale. And then harmful algal blooms, which are I've got a picture down there of where the water's washing in green. The harmful algal blooms kill humans as well as many animals, and we need to be able to predict those better. And then compound flooding, so flooding in and around the coastal areas. And then the second coastal oceanography area that we're looking at is predicting coastal fog. And then, if you notice, there was a turtle on our logo. It's because everybody loves turtles. Turtles are cute. And we're working on improving the prediction of cold stunning events, where turtles that are in the bay in Texas, it doesn't get cold very often in Texas. But when it does get cold, the turtles rise up in the water, and then the ships run them over, and then they're dead. And so if you can improve the prediction of that, they already have a preliminary AI system actually used. And if you can improve the prediction of that and then stop the traffic, then much more of the sea turtles will live. And so we're trying to improve that prediction as well. So it's another impact. So that was 2 parts of the cycle. The third part of the cycle that I think is key, because it's really what turns this into a cycle is the social science research, the foundational research in risk communication. So we're going to be using the risk communication to understand, to increase the knowledge and understanding of how the end users are understanding the trust in AI. People have asked me, how do you define trust? We're defining trust based on how our end users actually use the AI. We want our end users to understand it and to use it. We don't just want to develop AI that we just throw away. We want AI to be used. So develop models of how this attitudes and perceptions of the trustworthiness influence the risk perception. And then we want to take those methods and use them to inform the development of the AI so that it truly becomes a cycle, so that AI is developed for environmental science, tested with the risk communication, and that we generate improved AI methods. And so the risk communication, we're going to be interviewing key users. We've got, to understand what their definition is, what their perceptions are, what their definitions are of trustworthy AI. And on the next slide, I have a target population of some of these end users. We have a variety of different end users, that range from forecasters to emergency managers. And we will also include the general public through some of our collaborations with the private industry. So we'll be doing interviews and doing experiments and then feeding all of this data back into the development of the AI. And then I said in the beginning that we had 4 focus areas. So the 4th focus area is working on our workforce development and broadening participation plans. And we definitely are working on improving the diversity of the AI and environmental science workforce. The only part of this aspect, because I didn't want to spend the whole talk on just this, I wanted to give some research results. The part of this aspect that I wanted to talk about is our unique, so it's goal 4A. We're going to be developing an AI certificate. But the other parts, we're working on mentorships and broadening participation and putting a lot of training online. We get asked all the time, how can I learn AI? How can I learn machine learning? I've already got a job. How do I retrain? We're going to be putting modules online for K through 20. So that means all the way through university as well as workforce retraining. For the AI certificate, Texas A&M Corpus Christi is a Hispanic serving and minority serving institution, and they've partnered with Del Mar College, which is also a Hispanic serving and minority serving institution, and they are developing a level 1 AI certificate, which means 5 classes in AI. It's going to be AI for environmental science, and then that certificate we will take nationwide once we've proved that it works really well there. They'll be able to get a job directly from getting your certificate, but it'll also transfer to the university, so it can be a recruiting method. If you've got this AI certificate, then universities can accept those transfer credits and put you hire into their AI programs. For those of you who want to know who all's on the team, this is a picture from our proposal. I would like to get some more photos of all the people at the bottom as well, but the leadership team are the ones who are shown with actual pictures at the top there. So if you want to ask any of us, I'm all the way on the left-hand side, you want to ask any of us questions, if you know any of these names and you say, oh, I'm excited, I want to talk more about it, interested in learning more, partnering at something, any of these people are good people to talk to. Okay. I saved myself enough time, but I'm going to pause and say, are there any questions yet before I actually do research results?
Thanks, Amy. So we actually had one question coming from Bo Light, who's asking, environmental science is certainly not the only field interested in trustworthy AI. So how well do you expect this research to transfer to other applications?
That's a good question. I agree with that. There are lots of people interested in trustworthy AI, and I would assume that since we're focusing on creating physically based trustworthy AI, I think it will work to a variety of science and engineering applications. So I don't think that we're creating anything we are certainly focused on environmental science, but I think our results will generalize. NSF is funding us for the environmental science application. And by the way, so I'll one other note on that. NSF did require a domain. They required use-inspired research. So our use-inspired research is environmental science, but I agree, it will apply to other domains.
Great, thanks. I think that was the main question here. Thank you.
Okay, so what I was going to do, I have 2 halves to the research results. I'm going to go through them relatively quickly, but I can take questions halfway through. I wanted to talk just so you could see some examples of trustworthy AI, but these examples are done within my research group. So looking at hail prediction and then working on tornado, so the XAI for tornadoes. So the part that's red is the hail prediction, which I'm going to talk about first. And I know that most faculty start with this slide, I was waiting so that it was right next to the results, because this way I get to say thank you to my students who are helping to generate the results, but you get to see them right before I start talking about their results. So my research group, we work, my specific research group, yes, I'm directing the Giant Institute now, but, for 15 years, as he said in the introduction, we've been working on using machine learning to improve prediction and understanding of high impact environmental science phenomena. And I actually do research beside environmental science. It's just that that's most of what I talk about. And today, that's certainly what I'm going to talk about. So I'm going to just leave that there. The one that we're going to start talking about is hail prediction. And I'm going to assume that everybody knows what decision trees and random forests are, and just leave that up there for a minute and just explain where we're going with the hail prediction model. So the tasks that we're doing is to predict hail in the next 24 to 48 hours. We train 2 random forests. We also have a deep learning approach to this, but I'm not talking about that one today. I'm only going to talk about the decision tree one and the random forest one because it's much more mature. We train 2 different trees. The first tree, it predicts whether or not it will hail, and the second tree predicts given that it will hail. So all the branches that say hail, there's a second forest will go down and say what size the hail will be, because it could just be little peas that aren't going to do anything. It could be the giant golf balls you saw in the picture at the beginning. And why did we choose decision trees and random forests? Partly this is research it's mature research. We've been working on it for a while before deep learning was really shown to work on this. And we're just starting the deep learning approach for hail. But one of the things that random forests do that is really nice is that you can pretty much throw the kitchen sink at them and they figure out what really matters. And so that is actually good. And also there's already explainable AI methods that have been developed, trying to understand which features are most important out of a tree and then out of a forest. So our overall steps, I know that this is a very interdisciplinary audience, so I'm going to try to explain at the high level, sort of assuming you don't necessarily know the meteorology, but I am going to assume that the AI is relatively known, since that was my explanation of trees. We're going to extract the data from the numerical weather prediction model, train our machine learning method, and then, because I said this was the part we were going to talk about how we actually look at trustworthy AI, we've actually been implementing and testing this in the hazardous weather testbed, which is a unique thing that NOAA has at Norman, where you actually get to test new methods with real forecasters, but they don't go live. So if your method is doesn't work very well, then you're not hurting any of the forecasts. But if your method's great, then eventually your method can transition into the forecasting. So we have 2 papers there, as well as a third one under review. So the models that we're building on for this work, we're using convective allowing models, and those are called convective allowing models, so you'd think that they might be high enough resolution to actually resolve the hail and the tornadoes, but they're not. In order to do a convection allowing model across the entire CONUS, that's the continental United States, they're doing it at 3 kilometers. That's still a really high resolution, but it's too low, it's too coarse in order to be able to resolve hail. So machine learning can be used to predict those missing hazards. And also, sometimes the models correctly identify there's going to be a severe storm, but they're off by spatial or temporal, and the machine learning can learn to correct that spatial and temporal forecast error. And so for those who actually care about the details about which model it is, I have the models listed down there, but I'm just going to leave that. What we're doing, this is a picture from one of the models, the href models. You've got basically pixels of data. So we need to be able to identify the storms, then extract data from it. And because I said we're not doing deep learning, we're not using the image-based approach on this, we're doing statistics-based approach because we're doing random forests, we need to extract data for each one of those storm tracks. So taking a storm, what we do is we identify the storms themselves using a watershed method, which is just an image method that looks for pixels that are similar to each other. That identifies storms, and then within a storm, you can extract a bunch of statistics about that storm. So that's maximum, minimum, standard deviation of a whole bunch of variables. So that the wind, the updraft is the wind blowing up, the downdraft is the wind blowing down, reflectivity is the intensity of the precipitation, etc. There are about 500 variables that we extract, and so I'm not going to list them all here, obviously. The labels that we're using come from the radar data. So they come from the maximum expected size of hail, which is a radar-derived product. And the reason that we don't use human hail labels is that the human hail labels have been demonstrated to be highly biased towards cities and highways, as in it basically never hails in a field. But we know that it hails in a field. And so the radar-derived product is a little bit of an over-forecasting product, but it doesn't have the biases across the whole United States. So we decided that it was a better product. So having given you the details, I'm not going to talk about training and testing and validation and all that. If you want to talk about it offline, we can. But I want to talk about the human end of it. This is where I want to talk specifically about end users and how they matter. We were working on this product with the SPC, which was the Storm Prediction Center, and the SPC issues forecasts multiple days in advance of what they think is going to happen. Hail, tornado, wind, other storms. And they put out a wide area of very low probability. So you can see their legend on their forecast for this particular day is they have a 5%, a 15%, a 30%, 45, 60, and significant, which that just turns into a hatching, but it's not used very often. They almost never issue anything above 15%. Their probabilities tend to look like 5 and 15%. So the first time that we were testing this, our probability over here on the right, this is the machine learning model, all the black dots are hail. What you can see is our probabilities were much higher based on our scale. And we highlighted the vast majority of the areas that got hail. We did miss a little bit of hail, but not a lot. Our probabilities are much higher, but they didn't like it because the probabilities were too high. And we said, well, this is part of the trustworthy part. We need to make our end users happy with our model. So we looked at it and we went back and said, what can we do about this? And the first thing we did, so that was 2018. 2019, what we did was we calibrated our probabilities. We didn't retrain the model. Well, we did because we had another year of data, but we didn't change the process of doing the model. What we did is once you had the random forest probabilities, we then recalibrated them, just adding another machine learning model on top of them to bring them in line with more of what the Storm Prediction Center actually wanted. And what does this actually look like? This is a reliability diagram where if you're if you were perfect, you would go along the y equals x line. And this green line is one of the machine learning models that's been calibrated, and it is pretty much following that y equals x line. Again, there's not much up here, but that's because they don't ever issue anything above 60%. And then the version that was uncalibrated is the blue line. And so you can see its probabilities were nothing like what they should be for the reliability. And that's for 25 millimeter hail. We also have broken into the 50 millimeter hail, which is a larger hail, but it's a much more rare event. We talked about rare events in the beginning. And so the probabilities are reliable for small probabilities, but then we just don't have enough events at the higher probabilities. And if you'd like verification statistics, this is the equitable threat score, and then down here is bias. This is 25 millimeter hail on top, 50 millimeter hail on the bottom. And the calibrated version had much higher bias, so you want to have lower bias. So the calibrated version has the lower bias, the uncalibrated has the higher bias, and it has a better equitable threat score. So it's looking good. But we were still unhappy with what it was doing, and so what we tested in 2020 was actually to try to bring some of the physics into the model. And the way that we first thought to bring the physics into the model, since a random forest really doesn't have physics in it, was to look at the data itself and make the observation that hail differs by season, it differs by region, and the training data is very, very limited. Every time the Weather Service changes their model, we have to start over because they don't retrain it historically. They only just give us a new model from scratch. So we only have a couple of years of hail data. And so we wanted to use that data to maximize what we were doing and try to improve trust. And so what you get out of this graphic that's over on the right-hand side is showing that how the hail is moving over time. So what we did was we tried a couple of different responses, and I'm not going to show them all here. I'm just going to show one. The one that we're looking at is we took the idea of weighting the examples based on the month that they happened. And so this is just a graphic of what the weights look like, but this is probably the easier graphic to look at, which is that you have all of the data available to your random forest, but you weight the examples such that you care more about getting the ones right that are more recent. And so for May, this is showing of the size of the dot and the darkness of the dot tell you how much its weight is. For May, you have more. We didn't have enough. We just did May, June, July, and August. For May, you have one pattern of hail over in the upper Midwest. June, it moves to the farther upper Midwest. July, even further so, and then August, you can see there's just not very many examples. But if you want to see, how does that actually compare? You just created this thing. How does that compare to reality? This is from another paper, a Centennial et al. Paper about climatology. That means that they counted how often the hail happened, and this is about 15 years of hail reports, and they used the radar, and they're just giving you a graphic of how the hail falls, and the higher colors are the more likely to see hail regions. And if I flip back and forth between these two graphics, what you can see is that our weighting system that's just using time is finding the spatial patterns that also exist, and it's matching the climatology, even though they had 15 years of data and we have 3. And so the question is, okay, we just retrained our system. We kept the calibration, the regression system, and all of that, the random forest. How well did it work? Well, it worked really well this year. So this was tested in the hazardous weather test bed in the spring of 2020. And this is my favorite tweet for this because Adam Clark is one of the people who helps run the Storm Prediction Center. And he said, AI could be a game changer for this because he really liked how well the random forest was, this calibrated random forest was predicting the hail. And there will be, we have, more objective evaluations coming out. We have 2 papers that we're working on, so there'll be more results coming soon. And I did that fast enough that I can do the next section, but I want to see if there are questions on hail before I actually talk about XAI for tornadoes. No?
One of them is like, what kind of quantitative evaluation do you use for data sets for Trustworthy AI, especially when you're using explanations? Like, is there any quantitative evaluation which you use?
So wanting metrics?
Yes.
The metrics really depend on the domain that you're in. So for the hail work, for example, we were looking at, I'll go back to our objective. Those are quantitative evaluations here, right? Because equitable threat score is a score that they use inside the Storm Prediction Center. Reliability diagrams are a score that they use. There isn't one single Trustworthy AI metric. It is actually something that we're supposed to work on, and part of the Institute is coming up with different metrics. But the metrics that we use right now are the ones that matter to the people that want to use the AI method. So if they measure it using one score, then that's the score we're going to look at because that's the one they care about. Because if you give them some other score, they're just not going to care about.
Okay. Thank you. And one more from Rebecca Turns. And I believe you touched upon it briefly in the couple of slides back. But regarding trust, you said that you will collect information by interviewing key users and the general public and feed this information back into the development of AI. So how will you do that?
Well, that's an excellent question. I'm going to say that since I'm not the risk communication researcher, I'm the director of the center. I don't have an answer to that yet. We're in the process of doing our site-wide kickoff and all of our meetings. It's all virtual, just like this is. And the risk communication researchers are leading the next talk in a week. I'm going to defer to say, I don't have the exact answers and I don't want to get it wrong. I know they have plans to do the interviews and they're working with mental models and things like that, but that's about my level of detail of their understanding because I'm the AI researcher. So.
Okay. So have you thought about how that'll go into your AI, I guess?
Well, yes. So, that's part of the mental model work, which I'm still learning about. But mental models are, based on what people are thinking about the thing. And so I'm looking to use the feedback of, okay, we didn't trust this because, I can go to our hail work in that sense that's without the risk communication researchers because it's preliminary work, but where they said we didn't trust this because it was the probabilities were too high. So we're looking to look for things like that, like here's your XAI method, but it's not physically plausible. So what can you do to improve the physics of this so you can show us that it's actually going to work? Right. And that it's going to be based on what the end users say. I know one thing that's important to environmental science end users is how do things work in extremes. So how does not just extreme weather, but like in days of extremes. When it's really, really hot, does your model go crazy? When it's really, really cold, does your model go crazy? So, can we demonstrate that it works in extremes? So those kinds of things, as we do the interviews and as we show them how it works, we're going to get that human feedback, and that's what we're going to use to improve our models. But I don't have. We've been in existence for 3 weeks, so that's an excellent question, and I will have better answers with more depth in probably 6 months.
Great, thanks a lot, Amy. Okay, I think that's it.
Okay. So I will. I end at 150, right, or 250, right, for you?
You can take more time after that.
Oh, okay. Yeah. I just wanted to show some examples of XAI as well. So that was sort of the trust end, and then, went too many slides. The XAI end, I can do it relatively quickly and just answer questions on it. This is just another example of how we're looking at the XAI. And when I said we were talking about the XAI at the beginning, I said that those 2 results I could talk about more. This is work from my students, so that's why I can answer better questions on this because I understand this one better and I'm learning the other stuff. So the question for the tornado prediction, the research question we had was, could we develop an AI model on the data available in real time to improve tornado forecasting? And that on the data available in real time matters, because it isn't so much that you want to develop a model that, that takes an hour to run, but tells you whether or not there would have been a tornado an hour ago. That's not useful. We want to develop an AI method that the researchers are going to trust, but that will improve tornado forecasting in real time. And I said in the beginning, tornado forecasting hadn't really improved over the last decade. So I grabbed some results from this from a recent paper from Brooks in Korea. And the top one is showing the probability of detection. So if there's actually a tornado, did you detect it? And it's by scale of the tornado. So the larger scale tornadoes have a much higher probability of detection, and that has been improving, but we're still not getting where we want to get, especially for the lower scale tornadoes. And then if you look at the lead time, which is the second graph, this is like 1985 to 2016. I think it's 2017 because the paper is in 2018. It hasn't changed. Like, we would like to increase that lead time, and we would like to decrease the false alarms, and then we want to produce trustworthy guides to the end users. And so the approach I want to talk about is to train a deep learning model, and it uses the radar observations and the environmental soundings. So this is my giant graphic on the CNN and what data it took in. We had storm-centered radar data across the United States, and we have three-dimensional data, which is actually really cool. Because it's not something that people are going to process in real time. We have 4 different variables from the radar: reflectivity, spectrum width, vorticity, and divergence. And for the computer scientists, reflectivity is basically a measure of the precipitation, the spectrum width, and the vorticity and the divergence tell you different things about the wind. And hiccups. I'll leave the technical details for that for later. But just basically, you're taking in a whole bunch of 3-dimensional data about the atmosphere in real time, and then trying to predict, using the CNM, whether or not that particular storm will produce a tornado in the next hour. And so we had 12 different heights, and because this graphic is already complicated enough, we use this same graphic when we're trying to explain CNNs to audiences that probably have not seen deep learning. So we're trying to show what the convolution does to the graphics. I couldn't show you all 12 heights, but we have all 12 heights for all 4 variables. And then we also have something called an environmental sounding, and you'll see that in an example in a minute. The data is pretty high resolution. It's 1 kilometer data, 0.2 degree by 0.02 degree by 1 kilometer in the vertical. And it is actually available online if other people get excited about this data. The GridRAD data set is available online. We have to process that data, as I talked about with the previous, with the hail data. We have to process the data. This one we're taking deep learning, so we're doing more of a image-based approach, but we still need to be able to understand, when a storm produces a tornado and when it doesn't produce a tornado. And when you just have a blob on your reflectivity, how do you know which blob actually produced a tornado? So again, we're looking at watershed to break those blobs into storm cells, and then we're tracking. We have 5-minute data, and so we're tracking. This graphic is showing as we're tracking the storm every 5 minutes over time, so that you can associate, because storms change, they grow, they morph, they disappear, they merge. You need to be able to say, this is what one storm over time. And then we also, this is an example of a proximity sounding. It's if you've ever seen the weather balloons go up, it's what they're measuring the height, the wind and the temperature and the humidity, the dew point, as it was a measure of the function of the height in the atmosphere. So they graph it as the pressure, but it's just height in the atmosphere. So it's those balloons that you see go up, and they go up very, very coarsely. So if we're talking about data and how data is available, these are launched around the United States, but in a very coarse sense. So there are 2 of them that go out in Oklahoma, for example. And then they only do them twice a day, unless they're doing a special one. And if they do a special one, then they've done 3 times a day. So they're very temporally and spatially coarse, but they're still very useful data. So now, in the beginning, I was talking about how data is rare events, and tornadoes are very, very rare events. Even if you break the tornado into each individual 5-minute segment, you still don't have a lot of tornadoes. Our training set from 2012 to 2014 has 3,575 tornadic storms and 40,000 non-tornadic storms. And our validation data, pretty similar. We chose 2011 as a testing data because 2011 was kind of a bumper crop for tornadoes. But what we had to do so that the model would learn anything was to do data augmentation. And this brings us back to the physics-based needs, because you can't just randomly do data augmentation. This data means something physically. And so we did a little bit of translation where you translate the data, north or south or east or west. But then we did a little bit of rotation. But when you rotate a storm, physically you're doing something to what's happening in the atmosphere. And so you can't just take a storm image and flip it. It doesn't work that way. Then you have a storm that's not physically plausible, and so you're training your network on something that's not actually useful. So we looked at just minor rotations. And as it turns out, plus or minus 15 degrees was plausible. But if you did any more than that, then you got something that just couldn't be created in the atmosphere, and so it wasn't actually useful to train on. And then finally, we added random noise to the data. But again, you have to pay attention to how you're adding that random noise so that you don't make something that's completely unrealistic. We did find, by the way, that adding all of this data augmentation definitely improved the robustness of our model. So how well does it work? I was asked about metrics a minute ago, objective metrics. These are some examples of some objective metrics. And then, the question a few minutes ago was, what metrics are you using? And I said that it depends on what the forecasters care about. Everybody cares about something different. That's the interesting thing. There are probably 40 different metrics out there for atmospheric science. This one on the left-hand side is an ROC curve, which is a typical one that you see in AI. So you're looking for the area under the curve. And the area under this curve is excellent. We're in the 0.93 range. And that's with bootstrap resampling, so you can see confidence intervals on it. It's good. This is probably less of a common diagram for AI. It's a performance diagram. And so instead of an AUC where you want to be perfect by going up to the upper left, this one you want to go up to the upper right. But the area, you would still want the area to be 1. And so this is still a really high score. For tornadoes, I know 0.41 on an AUC diagram would be considered terrible. Not terrible at all over here. It's actually a really good score. And then you also want, this diagram also can tell you how biased you are, and our data the nice thing about this is that we are very unbiased because this is the 1.0 line, the y equals x line. And in the name of time, I'm going to skip this part. I'll skip this part just to say that it works well. We did an evaluation over hours, and then we did an evaluation over space, which I will talk about briefly because I think it's interesting. So upper left has the number of examples of the tornadoes, and a number of examples of tornadoes. And then we have 4 different performance metrics: the area under the curve, which is the one I just showed you, CSI, which is one that tornado forecasters use, probability of detection, which is whether or not you actually forecast the tornado if it actually happened, and then the false alarm rate, which you'd like to be low. So you want POD to be high, you want false alarm rate to be low. And what we got out of this is to say that we have very nice AUCs. It's very strong. The CSI is pretty decent, given that CSI is never super high on tornadoes, but it is worse in areas where there's fewer tornadoes, which is not particularly much of a surprise. But the key part that I want to talk about this, to bring us back into the trustworthy AI, is to talk about how we're actually digging into what the model actually learned. And I'm sure that others who are XKCD fans like me have probably seen this cartoon. But, I like this cartoon because this is the public's view of what machine learning is. It shows up on the news, AI, machine learning. I had a news interviewer a couple days ago ask me what AI was, and wasn't it going to be Skynet, and wasn't it going to kill all of us? And I'm like, no. I had to explain that. People think, okay, well, this is your machine learning system. Yeah, you just pour the data into this big pile of linear algebra and collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. Well, that's not really what we're doing. So looking into the model, we're going to look into the model 2 different ways. And I swear I'll end in like 3 minutes because I'm trying to be on time. I just want to tell you sort of 2 different ways to look inside the model. We have a whole bunch of ways and a bunch of papers on this, but I just wanted to show you the 2 first ones. The first one is saliency maps. So that just basically tells you the gradient of the model activation with respect to some input value. So we're looking at, what is most important to predicting an actual tornado. And we're going back to those graphics of different levels of the reflectivity. And the cool thing is that we can see things that are very, very physically plausible. So it tells us that our model is learning something that's physically plausible. The probability of tornado increases as you have a stronger rotation. Vorticity is a measure of instantaneous rotation. So it's a stronger rotation in the lower levels. It's increasing with the spectrum width, which has to do with the spread of the winds. It's increasing as the storm grows in height because the more severe storms are higher in the atmosphere. And those are all really nice and physically plausible, so it's nice to be able to see those to confirm. And then the second way that we looked at it is called backwards optimization or feature optimization. And the idea of this is that you can take that, you can create some sort of synthetic input example, and you can use that synthetic input example to learn what it is that maximizes your model or minimizes your model. And what we did was we took tornadic examples and we tried to turn them into non-tornadic examples. So given a tornadic example, what would the model have to do to that example to make it non-tornadic? And it took we did this over 100 storms, the 100 best hits. And it took the probability from 99.2% to 6.9%. And here's the original. This is the tornadic storms. This is what it created. And what's interesting is it doesn't visually look like it changed it all that much. What it did do was it severely decreased the height of the storm. So it made the storm less severe at the higher part of the altitudes. And then you get down to the sounding, and this is where it gets really interesting physically, because you get down to the sounding and you say, here's the original sounding. What does it look like? Well, it's a little bit different. This version that I showed you was when we had physical constraints in. This version was when we didn't have any physical constraints. And if I just flip back and forth, you see how jagged that sounding is? You may or may not know what a sounding should look like, but they should look something like this, smooth. This is not what it should look like. And so when you try to show a forecaster or emergency manager or anybody, a scientist, a model that learns, and you say, this is the optimal non-tornadic storm, they look at that and they say, that's not a non-tornadic storm, that's junk. And so it's a call for trying to make a better version of this. This was our first start at it. This is an improved backwards optimization with physical constraints built in, but we need to continue to improve that. And I think that's it. I told you I'd end on time so I could do questions. Those are my usual acknowledgments. I will leave that up for a minute because those are some papers that you can find more.
Great. Thank you, Amy, for that talk. So we have another question from Conan Kao, who asks, will your model predict hurricane chances, scale, and direction it heads, and use any of the hail, storm, hurricane, tornado throughout past decades to predict the extent of climate change and find key factors which explain or affect climate change?
Okay, that's a big question.
Yeah. Do you want me to repeat it?
No, I'm going to stop sharing. Then I can actually see you and I can actually see questions too. Okay, I'll answer it in halves. We're not predicting we're not particularly focused right now, at least, on where hurricanes are going, because the hurricane track prediction is already really, really good. The National Hurricane Center is really good at their job. The hurricane part that we're looking at is trying to understand the science of the hurricanes, trying to build AI models in particular that will improve our understanding of the structure of the hurricane, so we can improve the prediction of whether or not it's going to intensify quickly. Okay, that was half the question. There was another half of the question that was about climate change in hurricanes and hail in hurricanes. If I can see it again.
Right.
Yeah, go ahead.
Can you use any hail, storm, hurricane, tornadoes through the past decades to predict the extent of climate change and find key factors for that?
So how much climate is changing using the hurricanes and the hail? So looking at all the extreme events. Yes.
Yeah.
Yes, I think you can. It's a big debate in the community. Exactly. Because climate and weather are different, right? So we're all agreeing that climate is changing. We all agree there's an impact on the weather, but figuring out exactly what caused that particular tornado or that particular hailstorm or that particular hurricane is awfully hard. Saying that one was caused by climate change is hard. So, and that's not something that we were planning to focus on. We were planning more on the fundamental research of just trying to understand, given the storm is here, how can you improve its understanding of that storm?
Okay. I'm
not saying that's not important. And long term, yes, I would like to do that. But right now, within the scope of our funding, $20 million is a lot of money. But on the other hand, it only goes so far.
I guess I had another question here. So have you, in your course of your research and your approaches, have you found a situation where the machine learning performance is very good, let's say in terms of AUC, but somehow it is not good for the weather domain experts, right? So maybe there's something missing. Sorry.
Yeah. I wouldn't call it something missing, but the first version of our hail research, all the objective measures were beautiful, and they didn't like it. So the end users didn't like it because it wasn't fitting what they wanted and their needs. And I've had other people tell me, well, why didn't you just tell them to adapt and learn to use the model? I'm like, that's not the point. They've been doing it their way. And another end user might want something different, right? We need to develop what they need. But, objectively, it was scoring pretty well. It's doing better now, by the way. But, even then, it was doing well. The tornado work might fit into that too. Right now, the tornado work, I said that our goal was to do this in real time, but we haven't fielded it in real time. We actually just got funding to do that. So ask me that in a year. But, objectively, the tornado works really, really good. So
Right.
whether or not it's going to work with the actual forecasters, I don't know yet. But that we're going to know that, in addition to our AI center, we also got funding just to operationalize that product. So NOAA has a program called the Joint Technology Transfer Initiative, and we just got funded to operationalize that tornado product. So we'll be able to know whether or not it really meets the end user needs. But that funding started September 1st as well. So
Okay.
I don't have it operationalized. Our goal is to test it within a year.
Right. So we have another question while you were giving that answer. Is the National Center model based on machine learning as well?
Oh, the National AI Center?
Yeah.
Certainly, we're using AI as the broader term. So I'm using
I think I don't know whether Conan meant that or probably I think probably he meant the Innova Center, right? Whether it is based on like using machine learning as well. I think the national model, I guess. Otherwise,
well,
maybe Conan can specify what.
yeah, because there's a NOAA AI Center too.
Okay, fine. So maybe
If
we'll
that,
come back to that if Conan explains what he or she had in mind. So Srijan Kumar also asked one question, which is a follow-up to what I had asked. What did you do to adapt your model to suit the end user needs? So I guess you had given a couple of examples. Maybe you want to elaborate.
Right. I mean, I've given a couple of examples. One where we changed the probabilities. With the tornado work, what we ended up doing was adding physical constraints to the beginning of the end user needs, was just showing them, here's what the model learned, and them saying, that's not physically plausible. So we're trying to put physics into the model to make sure that it can't learn something that's physically implausible. It's going to get deeper than that. I mean, that's the beginning of it. So.
Right. There was another question by Alexander Rodriguez who asks, I wonder if data from other countries is relevant for training models in these applications.
I think so. I mean, I've got a student who's just starting to work on predicting convective initiation, which is the start of thunderstorms, and the data he's using is global. So, I mean, I don't see any reason why we can't use global data. It's just the examples that I had, the data that we had available to us is from NOAA, and NOAA is only the United States.
Okay. Yeah. So coming back to Conan's question, so Conan had in mind the NOAA, NOAA thing.
So there is a NOAA AI Center, and I'm involved in it peripherally, as in I'm working with a lot of NOAA researchers, many of whom are working on starting that up. But ours is an NSF center. Theirs is going to be more focused on. Theirs is a very different model. It's a model for, it's like a dispersed center, and it's going to be workforce retraining and then helping to provide expertise on AI throughout NOAA. But they're going to be working with us as well. We're actually in the middle of trying to sign the lawyer level agreements so that they can actually work with us as well.
Sure. Great. I think that's all the questions there are here. Thanks again, Amy, for your time and for the great talk. And I'm sure you can't hear everybody clapping, so at least I will clap for you.
Thank you.
Thank you for giving the talk. Take care.
Thank you.
Bye. Bye, everyone. Yeah.